Hello friends, welcome to another video on data structure and algorithm. In this video we'll be learning about binary tree data structure. But first let's see what we have learned in linked list. In linked list we have learned something called a node, which has two part, data part like int, char, double float, and a pointer part which points to next node in a memory. You can see here. And look at this third node. This third node is not pointing to any other node, so in its next part we simply store a null value. So this is structure of a node, and by joining this node we can create a linked list. So this node has two part, data part and a pointer of type struct node which hold address of a node. Now using similar concept, let's try to understand what is a tree data structure. In tree data structure we have node like linked list. Its one part hold value like int, char, double float, but here only difference is we have two pointer, left pointer and a right pointer. So these pointer contain address of their next node. So they are going to point next node in memory, and in similar way these two node going to point some other node in a memory. Okay, if we don't have any node in memory, so we simply assign a null value to their pointer part. In this way we can represent our tree data structure. Okay, now let's see how its node structure look like. See, we have a data value and a left pointer containing address of left node and a right pointer containing address of right node. Okay, now we'll see what is a binary tree. So look at this example. This is a binary tree. And how would I know this is a binary tree? So look at very first node, which is 20. So it is connected to two node 10 and 25. You can see here 10 and 25, and value of its left node is less than its value and value of its right node greater than its value. And similarly for node 10, it is connected to two node and value of its left node is less than its value, right node greater than its value. And similarly for 25. Okay, so this is simple condition for a binary tree, and if you observe carefully, all the value lesser than root node are in left subtree, and all the value greater than root node are in right subtree. So using this amazing property we can do some operation like we can easily insert an element in a tree, we can easily search an element in a tree, we can easily delete any element of a tree, and we can easily traverse through complete tree. Okay, now we'll see how we can create a binary tree. So this is structure for a binary tree, and in order to create a single node I use this function create node. Okay, so this function returning me a node pointer. Okay, so it has address which is created by malloc function. So malloc function creating a node in a memory and it returning me address. Now I'm going to call this function. So I'll pass some value to it. A node is created in a memory and its address is returned. Okay, so using malloc function we create a node in memory. So initially it holding some garbage value, so we'll pass this value 25 to its data part. Okay, so its data part holding value 25 now, and a null value to its left and right pointer. Finally I return this node. Okay, so I have created very first node in a memory. In order to insert another node I use this function. It has two argument, so I'm passing address of this root node and some value to it. Okay, I'm going to insert another node having data value 10. So first I'll check is root equals to null. No, it is not equal to null, it has some address. Then switch to next part. Is value greater than data value? No, it is not. Then switch to else part and check is value less than data value. Yes, it is less than data value. So go to left part and now call this function again. So this is a recursive function. I'm calling this function again and again. So I'm inserting its address. Now you can see here left address is null. Okay, so first we are going to check is address equals to null. If root equals to null, yes, it is equals to null. So I'm going to create a node here. I'm calling that function, create node function. So a node is created here, and finally its address is returned to left part, and finally I'm going to return this complete root. Okay, so what basically I'm doing here, for example, I want to insert a number 12, for example. So first check, is 12 greater than root node? No, it is not. Then check 12 less than root node? Yes, it is. Then go to left part and again check, is 12 greater than 10? Yes, it is greater than 10. Go to right side and then check, is address null at this part? Yes, it is null. Then create a node here. So I created a node here and value is passed to its data part, and finally I return this complete tree. In this way I can insert any number of element in a tree. Okay, so now I want to print all these element I inserted. So for that I use something called traversal. I have to traverse through complete tree. Now I want to print all the element of this tree. For that I use Inorder Traversel function. First I am going to pass address of root node, and now node equals to root. Then check, is its address equals to null? No, it is not equal to null. Then again call this function and pass address of root's left node. Okay, now root equals to root's left node, and then check again, is address equals to null? No, it is not equal to null. Then call this function again, and I'm going to call this function again and again until I reach to a node whose address is null. Now address is null, so return to previous node and check, is address equals to null? No, it is not equal to null. Then print its data part and go to right side. So go to right node, here address is equals to null. Then came back to previous node and then previous node and print its data part. So 10 is printed, and then go to right side. Here address is not equal to null. Then go to left side, here address equals to null. Then came back to previous part. Okay, now go to right part, here address equals to null. Came back to previous node. Okay, then previous node and then previous node and print its value, and then go to right node. Okay, its address not equals to null, so go to left node, and its address also not equal to null, so go to left part. Now its address equals to null, so came back to previous part and then go to left part, its address equals to null. Came back to previous part and then previous part and print its value. Then go to right part, its address not equals to null. Then go to left part, its address equals to null. Came back to previous node and print its value. Okay, then go to right side, its address equals to null. Came back to previous node, then previous node and then previous node, and then out of the this function and take a deep breath. In this way I can print all the value of tree. So these values are in ascending order. Okay, now I want these value in descending order. To do that I have to change something in my code. I have to change second and fourth line. First we traverse through right subtree. Okay, so I have printed all the element of left and right subtree. Now I want to search an element in a tree. To do that I have very simple function here. Actually I am just comparing my key value to data part of all the node. Okay, so this is a tree and here I want to search an element 12, and to do that what I'm going to do, I'll pass address of this complete tree, I mean address of node and this key value, and then check, is address equals to null? No, it is not. Then check, is root equals to key? No. Then check, is root less than key? No. Then obviously it will be greater than key. So search in left part of the tree and check, is root's left address equals to null? No, it is not equals to null. Then check, is data value equals to key? No. Then check, is data value less than key? Yes, it is less than key. Then go to right side and check and again check, is address equals to null? No, it is not equals to null. Then check, is data value equals to key? Yes, it is equals to key. So I found what I was looking for. Okay, so now let's discuss what is time complexity for binary tree. Let's try to understand this with the two different examples. See, these two tree has the same number of data, but their root elements are different. Okay, so here I want to search element 30. So how many steps required in order to achieve this goal? Okay, if I'm talking about first tree, I need a 2 step, and for second tree I need 6 step. Okay, if there are n number of element in second tree, then I need n minus 1 step in order to achieve my goal. If I ignore a constant term, then I can say its time complexity is big of n. This is worst case ever possible in binary tree. Okay, now let's see what is time complexity for first tree. Here its time complexity is log of n, where n represent number of element present at particular level. For example, at level 0 I have one element, at 1 2 element, at 2 4 element. Okay, and 30 is at level 2 and its n value is 4 because there are 4 elements. Here n value is 4 and value of log of 4 will be 2, so I need a 2 step because base is 2 here, so I need 2 step in order to find 30